1110, we're talking about Taylor and Mclaren series. So right here, this is a Taylor series. Right here, Taylor. And Mclaren is when A is equal to 0. So with Mclaren series, it's a special version of the Taylor series where these minus A's are not there. It's just x, x squared, x cubed, and so on. Okay, and this will, when you have a Taylor series, it will converge in an interval like this. Okay, this interval right here goes from x minus a to x. Wait a minute. What am I thinking? No, it goes from a minus r to a plus r. Okay, because to do this, you get x minus a less than r but greater than negative r, and then it just goes to that. Now, and then it could converge at the endpoint at one or both of the endpoints. So, but you got, or maybe not, and you gotta check that. Usually, check the endpoints individually. Okay. So now, last time we sort of did these questions here last time, and if you take this equals all this, if you set x equal to a, then okay, that x gets replaced with an a, and then these x's all get replaced with a's, but they're going to just go away. Okay, so C0 is f of a. Okay, and then for C1, for this one right here, C1, we take the derivative. And the derivative of the left-hand side is f prime of x. The derivative of the right-hand side, this goes away. You're just going to get C1 plus 2, C2, x minus a, and so on. And then you set x equal to a, that gives you f prime of a equals C1. So C1 is f prime of a, would be the answer to this question right here. Okay, whereas this C0 is f of a. And if you continue the process repeatedly, okay, so then at the next step, you're going to get the second derivative at a is equal to 2 C2. So C2 would be the second derivative of a over 2. And in general, what you're going to get, in general, is that Cn is the nth derivative at a divided by n factorial. Okay, so that's kind of how that works. Now, one thing that you assume when you look at this is this has to be true for all values of x. So you can pick individual values of x and set them equal to different numbers, like a, for example, here. And it should work out because it's true for all values of x. Okay. So on the next page, we have the summary of that. And here are here's the formula again right here of what the terms are. So let's do an example here. It's the homework. So number 1, fn of 0 is n plus 1 factorial for n equals 0, and so on. So that's giving you this derivative part right here for the Mclaren series. So Mclaren series, again, that means that a is 0, Mclaren series. So our CNs are going to be the nth derivative at 0, because a is 0, all divided by n factorial. And because the nth derivative at 0 is n plus 1 factorial, that's just going to be n plus 1 factorial right there, divided by n factorial. And what is n plus 1 factorial divided by n factorial?
Just n plus 1 on the top right.
Exactly. Now let me go through this. Let me do the details of that. So n plus 1 factorial is n plus 1 times n minus 1 all the way down. Okay, all the way down to 2 and then a 1 if you want. N factorial is n times n minus 1 and all the way down to 2 and 1. And so all of those are going to cancel with all of those, and you end up with n plus 1. Okay, so that's n plus 1. So our CNs are n plus 1. Therefore, you just plug into here, and you have n equals 0 to infinity of n plus 1 times x to the n. Okay, so you're just setting Cn equals n plus 1, and a is equal to 0 in this formula here, and that's what you get for the first part. Okay, now it's also asking what's the radius of convergence. Okay, so find and its radius of convergence. So we also have to find out what the radius of convergence is. And we don't know what the original function, it doesn't tell us what the original function is, although maybe you could figure it out, maybe not. But we can use either the ratio test or the root test to figure this out. So if we go ratio test, there's a couple of different ways to apply the ratio test. One of them is to take R is the limit as n goes to infinity of the coefficients Cn over Cn plus 1, like that. So that's the limit as n goes to infinity of, and then Cn is n plus 1, and Cn plus 1 is going to be n plus 1 plus 1, so that's n plus 2. And that's going to go to 1, so the radius is going to be 1. Okay, that's one way to do it. Another way to do it would be to argue this way. Just go back to what we did before. And this is an plus 1 over an. Just to calculate this L. And an plus 1 dot, and this way, and this one right here, which is the original radius of convergence, we use these as the a sub n. So the c sub n is just the coefficient. A sub n is the whole thing. Is the whole thing in the series. So that would be c n plus 1 x minus a. Wait, let's go ahead and substitute everything in here because I don't have much space. So look at this one instead. So it's this whole thing right here. So a n plus 1 would be n plus 2 x to the n plus 1. That's putting n plus 1s here and here. And then just putting a sub n right here and here would be n plus 1 times x to the n. And as n goes to infinity, this part right here goes to 1, and you end up with just the absolute value of x, because this xn plus 1 over xn is just x. And this will converge when L is less than 1. And so then from there, we can deduce that the radius of convergence is 1 as well. That's another way, just a separate way to do it. Any questions on this?
Nope.
Great, let's go to the next exercise, number 2. And here you're supposed to find the first 4 non-zero terms of the Taylor series for f of x equals 5 cosine squared of x, centered at a equals 0. And so in this case, we have the actual function right here. And we're supposed to find the Taylor series. And a is 0, so that's going to be 0 there. So one way to do this, sometimes you can, if you know different series, you can do some manipulation and figure it out that way. If not, then, because later on I'll give you, so like, what I mean by that is later on I'm going to give you a list of a few different series and what their, a few different functions and what their Taylor series are. And then if you do slight modifications to those functions, then sometimes it's just a slight modification to the Taylor series to come up with the Taylor series for something that's slightly different than something that's on the list. And we did a little bit about that last time with the series, with the geometric series, 1 over 1 minus x, and making changes to that, derivatives, integrals, replacing x with 2x, replacing various different things, or multiplying by stuff. There's a lot of stuff you can do that way. But in this case, it's not something that we have. So what we're going to do here is make a little chart here. So I'm going to have n, and then I'm going to have the nth derivative, and then I'm going to have the nth derivative evaluated at 0, because a is 0. Okay, so that's 0. That's why we're going to take the nth derivative at 0. That's why that's important. And then, and that's getting us to here. All we'd have to do is take this and divide by n factorial. So we just put that over n factorial. And then that will give us these Cn's. Okay, now of course when n is 0, it's just the original function, 5 cosine squared of x. And then you plug a 0 into here. Cosine of 0 is 1. So cosine squared is 1, so that's just going to be 5. And that's going to be 5 over 0 factorial, which is just going to be 5. And then we can do another one, which is the term, which will be 5 times 1. That's 5. 5 times this to the 0, which is 1. So this is just the constant term. Now, it's easier if you take this function here. Let's concentrate on that for now, for a minute. And there's a double angle formula. The cosine 2x is equal to 2 cosine squared x minus 1. So that means that 2 cosine squared x is equal to cosine 2x plus 1. That's just adding 1 to both sides. So this is a trigonometric identity, the double angle formula. One of the double angle identities right here. And I'm just manipulating around that. So 2 cosine squared x is cosine 2x plus 1. Therefore, 5 cosine squared x would be 5 cosine 2x plus 5 all over 2. Okay, so dividing this by 2. So basically, you can replace this with 5 cosine 2x over 2 plus 5 halves, and that gives you 5, and that's still when n equals 0. So you're going to have just, your term's going to be 5. Okay, but the reason I did that is because that's going to make our differentiation much easier, because the next thing you have to do is go to when you have to go 1. So when n is 1, that means you got to take the derivative of this. So take the derivative here, and the derivative of cosine is negative sine. And then by the chain rule, you have to take the derivative. You have to multiply by the derivative of this, which is 2. So that 2 is going to cancel with that 2. So you're going to get negative 5 sine 2x. And when you put a 0 in here, sine of 0 is 0. So that's just gone. That's just 0. Now, unfortunately, it says they're looking for non-zero terms. Okay, so that's 0. And so this is like, oh, I'm so sad about that. Or maybe you could, or maybe you would think, oh, it's great. Well, it means just we get to do more of this adventure. Okay, so let's do the next derivative. So take the derivative of this, and derivative of sine is cosine, and a 2 comes out, so that's negative 10 cosine 2x. And when you put a 0 in, you're going to get negative 10, because cosine of 0 is 1. And then you're dividing by 2 factorial, which is 2. So that's going to be negative 5. And you got to multiply by x squared. Okay, so it's x minus a is 0. And then n is 2, so it's squared. So that's going to be our next term. So let me make a list of the terms right here. So there's 5, and then there's negative 5x squared. We need 4 of these. Oh, okay, so and 3 is going to, when you take the derivative here, that gives you positive 20 sine 2x. And maybe we'll just go on a derivative thing. Okay, so the next derivative is going to be 40 cosine 2x. And the next derivative is going to be negative 80 sine 2x. And the next derivative is going to be negative 160 cosine 2x. Okay, so I just did a few derivatives here. And then when you plug 0 in here, that's going to be 0. This is going to be 40. This is 0, and this is negative 160. Okay. So unfortunately, those are going to be 0, so boo, they don't count. But this one here, it's 40 divided by 4 factorial. And that reduces down to 5/3. So your term is 5/3 x to the 4th, because this is 4. Let me draw a line there. And then this one is negative 160 over 6 factorial. That reduces down to negative 2/9. So this is negative 2/9 x to the 6th. Okay, so my third non-zero term is 5/3 x to the 4th, and my fourth non-zero term would be negative 2/9 x to the 6th. Okay, you guys have any questions on that one? So once again, also that and that are 0 as well. So they don't count, but that's 1, 2, 3, 4 terms. So let's move on to the next exercise then. Number 3. So notice here, this is how we find some, that we don't know for sure. And here, now one thing I'll point out right here is you can look for patterns here. You can look for a pattern of what's going on here. And generally, when looking for patterns, here it's kind of hard to tell. You got negative 5, you got 5, negative 5, 5/3, negative 2/9. Where does that come from? That's just kind of weird. Okay. But if you're going to look for patterns, then what you would do is look at this, right? You'd look at 5 over 0 factorial, negative 10 over 2 factorial. So you change that back to factorial. 40 over 4 factorial. 160 over 6 factorial. Then you can see that there's a pattern here where each time you're multiplying the numerator by negative 4, and you are raising the factorial by 2. So this from here to here, it's 40 to negative 160 would be multiplying by negative 4 to get there, and then increasing this 4 factorial with 6 factorial. So you can look for patterns here, and that's kind of how these were come up with right here, all these different formulas. So here's the Taylor series or these are Maclaurin series for sine. And I put it in both forms where it's written as the in the summation, and it's written out. And here's cosine. And here's inverse tangent. The exponential function, e to the x, is this one. The log of 1 plus x. Now we did this one already. And we also did inverse tangent. Those can be derived from the geometric series. And then this is called the binomial series. So let me just say a few things about each of these. The sine, cosine, and e to the x, their radius of convergence is infinity. They converge everywhere. These three right here. And then inverse tangent and natural logarithm of 1 plus x. Those ones have a radius of convergence of 1. And then this last one is called the binomial series. And here the radius of convergence depends on the k. Okay, so if k were a positive integer, then this would actually be what we call terminating. You wouldn't have to go to infinity. It would just be a polynomial, not an infinite series, if k is a positive integer. And if k is negative, then that's a different story. The radius will, and then if k is a positive integer and it's just a polynomial, then the radius is infinity. K converges with all values of x. But if k is negative, for example, then your radius would be 1. So it just kind of depends. And it's not something that we're going to do a whole lot, so it's not really important. That's not really that important. But these three right here, these are really important. And it's nice that the radius is infinity for each of those. So let's use this information to do number 3. Okay, so find the Mclaren series for this one. And you'll notice that this right here is the e to the x one right here. So if e to the x is this, then e to the negative 6x, so the x has been replaced with the negative 6x. So then all you have to do is replace this x with a negative 6x and in parentheses. And that's what you get. So that's going to be your answer right there. And because this has a radius of convergence infinity, then this one will be radius of convergence infinity also. Now you can calculate the radius of convergence if you want, but you're going to get infinity because of this n factorial mainly. You have a power here, some power. This is geometric. This is factorial. Factorial is like overwhelms geometric. So if you have a factorial in the denominator and geometric, which is just like raising the powers in the numerator, then that's going to be convergent. If it's the other way around, then it will only converge. It will only converge at 0. The radius of convergence would be 0 if it was the reciprocal of that. Okay, just let me know if you have any questions. We'll do some more of these. I want to. So this is just like give them a little break there. Let's go back to this. Let's go back to. So this number 3 is kind of out of place, but then we're going to go back to this method right here with number 4. So here we have 8 over x. And the difference here is that a is -4 this time. So that complicates things. It's much, the Mclaren series is generally more easier to deal with. So, but again, we're going to do a chart here, n, and then the nth derivative of x, and then the nth derivative of x evaluated at -4, because a is -4 this time. So that's the difference. You're giving experience with different different values of a other than 0. So I think that's the idea right there. Wait, what the? Okay, so I'll make a chart here. I generally save more room for the function, although I guess I didn't need to, because I know that I would be able to deal with this function. If I want to take derivatives of this, it's easier to just write it as 8x to the -1. So when n is 0, you have the original function, and you put a value of -4 in here. That's going to be 8 over -4, which is -2. Oh, wait a minute. They want it in the general form. So if you're going to do the general form, then don't simplify it. Just leave it like that. Just leave it as a fraction. Don't simplify that. Because they want the answer like this. They want us to put something in there. They just want to answer like that. So that means we have to figure out what patterns to use. Okay, so now, then the next column that you want is the nth derivative at -4 divided by n factorial. Okay, that's just following this. That's just following this formula right here. So that's going to be 8 over -4 times 1 over 0 factorial. Okay, and that's when n is 0. So let me put the n here just for a good measure for 0. So what we want to do is we want to come up with. Oh, wait a minute. Instead of let me do one more column and then we'll put the n in. And this column will be the term. So by term, we mean, let me just choose a different color. By the term, we mean this whole thing right here. It goes there. Whereas this one, right, the previous one is just this is just c sub n, just the coefficient on the front of the term. So you just take whatever this is and add and x minus, or x plus 4, x minus a, so a is -4, so x minus a would be x plus 4. Okay, let's take a derivative. So when we take a derivative, you have a -1 come down, so that's -8x to the -2. And so this is going to be -8 over -4 squared, or -8 over -4 squared times 1 over 1 factorial, and then your term is going to be something like -8 over -4 squared, x plus 4. It's still going to be x plus 4 to the n over, but this is 1 factorial. Okay, and then the next term, when n is 2, you have a negative 2 coming down, so that's going to be negative 8 times, let's say positive times 2, x to the negative 3. So your nth derivative is going to be like 8 times 2 over negative 4 cubed. That's by putting a negative 4 in here for x. And this is going to give you 8 times 2, and then you have a negative 4 cubed, and you got this 2 factorial. Now, you might notice it at this point that 2 factorial is the same as 2, and those are just going to cancel each other off. Because, and you kind of see, they kind of look for a pattern here. When n is 3, you've got this negative 3 coming down, so this is negative 8. And this is going to be 3 factorial now. When this 3 comes down, you got a 3 factorial. You got this negative here, though. Okay, so that's going to be negative 8 over negative 4 to the 4th factorial, to the 4th, I'm sorry, times 3 factorial. And then here, the 3 factorial is going to cancel with this right here. So you're just going to get negative 8 over negative 4 to the 4. So now maybe you can see the pattern, maybe not. But let me see. Let's see what's happening. So here, the signs flip from negative to positive, negative, positive. But because we're raising negative 4 to a power, then when we have a negative up here, this is gone down here. But when we don't have a negative, we're getting a negative. So in the end, what's going to happen is what it looks like. It looks like it's going to be, you've got that negative 8 up there. And instead of negative 4 to the n, we can write 4 to the n, and then x plus 4 to the n. Wait a minute, when n is 0, this is 1. This is 1, and when n is 1, this is squared. Okay, so you can just add a plus 1 right there, and that should take care of that. Or if you wanted to, you could make this a negative 2 instead, and then 4 to the n, because you could do that as well. That would also work. So let's do that. And then just check that's going to work with all your terms. Any questions after this point? So you just have to like look for patterns. So then what could I say? Okay, so don't simplify. And look for patterns. Don't simplify everything. Sometimes it's good to simplify some things. Like for example, as soon as we figured out that these factorials will just cancel with this factorial, then that's good. We can just like ignore those from then on.
Why does it cancel with those factorials again? When we bring down the 3?
Because here you got a 3 factorial here.
Okay.
And this is going to be a 3 factorial in the denominator.
Why is it not just 3 when we bring it down? Why is it 3 factorial?
Because you have this 2 here. So when you take the derivative, a negative 3 comes down, and that's going to be 3 times 2.
Oh, okay.
And when you take this derivative, a 4 is going to come down, or negative 4 is going to come down. So you have 4 times 3 times 2. You have 4 factorial.
Okay.
Okay, so this should work right here. Now, for radius of convergence, we have to figure the radius of convergence. You can use the ratio test here or the root test. And on this right here, and you're gonna get R is 4 if you do that. But there's a slightly easier way. And that is if you look at, so here you have A is negative, you have -4 right here. A is -4. If you look at the function here, if you look at this function, let me get a different color, then when x is 0, this is not defined. That gives you trouble. No, it's not continuous, or it gives you trouble. That point gives you trouble. Usually, what's going to happen in this kind of situation is that if you take the distance between where you're expanding about, the distance between this A and this point here, so the distance between -4 and 4 is 4. And that's going to be your radius of convergence. That's another way to find the radius of convergence. Another way to do it, other than just that. Okay, there are some weird exceptions to that, and I will point that out when we get to, like, for example, with this binomial series. There's some cases here where it's just there's some slight exceptions to that, but because this one's just gonna have the radius depends on your value of k. There's some slight exceptions on that one to it, but that's about it. And you can also see right here that that it works right here, because when you put in x equals -1, you're trying to take the log of 0, and that doesn't exist. So that's one value away from 0. From 0 to -1 is the distance is 1, so the radius is 1. And same thing with the inverse tangent. Okay. So let's go on to the next exercise, number 5, unless there's any questions that anyone wants to ask about that one. Okay, so number 5, find the Mclaren series for 9x cosine of 1/8 x squared. So for this one, you can split up into 9x times cosine of 1/, or rather x squared over 8, and you just copy the cosine down, -1 to the n. But instead of writing x to the 2n, you take all of this, x squared over 8 to the 2n. Okay, so all of this goes in here. And then you're still dividing by 2n factorial, like that. And it's going n equals 0 to infinity. So you just substitute this x with x squared over 8. And then just try to simplify that a little bit. Okay, x squared to the 2n, that's going to be x to the 4n. And then in the denominator, you're going to have this 2n factorial, but you're also going to have 8 to the 2n, like that. And then we're going to bring the 9 in. You got to take this 9x inside the summation. Okay, first of all, the 9 just goes right there. You can just put that right there. Or you can put it out in the front, either way. If it looks better out in the front, then do that. Yeah, it probably looks better. It'll probably look better out in the front. So I'll put the 9 first. Okay, so we're just taking this 9 in right there. And then we're taking the x in as well. And what happens when you take the x in is that you take x times x to the 4, and you get x to the 4n plus 1. Okay, so that's what's happening there. So this is going in right here. X times x to the 4n, that's actually x to the 1. So that's x to the 4n plus 1, and that's going to go right there. And then you still have this and this. So 8 to the 2n. Now you can change this if you want. You can change this to, this is 8 squared to the n. You can split the 2 and the n up, so that's 64 to the n. So you could write it as 64 to the n. And then you've got this 2n. That's like the worst 2 ever. Like that. And so that should work. And the radius of convergence is going to be infinity, just because the radius of convergence for cosine is infinity. Okay, great. So there's that. And then for number 6, use the Mclaren series to find for e to the x to calculate 1 over the 10th root of e to 5 decimal places. Okay, so 1 over the 10th root of e is the same as e raised to the negative 1/10. Okay, so 1 over, that means that's going to be negative, and the 10th root is 1/10. So here you have, in this case, what you want to do is use this part of you want to use this format right here. So e to the x is 1 plus x over 1 factorial plus x squared over 2 factorial. But x is negative 1/10. Okay, so 1, there's this 1 right here, plus, and then negative 1/10 over 1 factorial. And then x squared would be negative 1/10 squared over 2 factorial. So you're just putting negative 1/10 in for these x's. And if you sum up, let's see here. Let's see, what's the next one going to be? negative 1/10 to the 4th power over 4 factorial plus negative 1/10 to the 5th power over 5 factorial, and so on. So that's 1 minus a 10th. This, when you square it, it's going to be positive. And 1/10 squared is 1 over 100. So I'm gonna write it this way instead, 1/2 over 100. And then the next one, when you cube it, it's going to be negative. So I'm going to write over 1,000 instead. So that's 1 over 3 factorial, which is 6. And then the next one is, this is 10,000. 1 over 4 factorial is 24. And then 5 factorial is 125. Wait a minute. No, it's not. Is it? No, it's 120. Okay, so if you put all those terms in the calculator, you get approximately 0.904,837,4167, approximately. And if you were to do another term, this would be 1,000,000 down here. And this would be even really small too. So you'd have 1,000,000 in the denominator, and this would be really small. So it says 5 decimal places. That means that really, all we really needed to do for 5 decimal places, all we really needed to do was go to here, because this is 5 decimal, because this is 6, this is in the 6th decimal place. And then 120 puts it, oh, even in the 7th or 8th. This is really small right here. Okay. So really, we just only need to go to here. Because this term right here, if you calculate that one, so that's 1 over 120, oh wait, over 12 million. Which is about 0.00, like you got 7 0, 1, 2, 3, 4, 6, 7 zeros and then an 8. Like that. So that's already